All right. Hey, everybody. So we're here for our last lesson of this particular unit. This lesson it's going to be on the longer side, so I apologize right now. Go get yourself a snack. I just didn't want to break it into two more videos. I figured I'd just put it into one. But anyway, like I said, go get yourself a snack, get yourself comfy, maybe sit outside. It's a beautiful day. Just no COVID, right? Stay inside. Just stay someplace safe. Anyway, this is all about energy and pretty much how it relates to work. So we're going to do work and energy theorem, different types of energy, and then a little bit at the very end about collisions and energy and how that's related to this kind of stuff. So first part about this is we're doing a little bit of chapter 10 and 11 kind of combo in here, a couple of the key points. So if you're trying to figure out, follow along in the book for some reason, it's going to be in a couple of different spots. So anyway, there you go. So this part, talking about work and energy, is the first part. The last unit was all about work. Work equals force times distance. And as we're kind of moving into this section, most people already kind of know that idea of what energy is, that if you do work on an object, that somehow it's related to energy. We talk about, putting energy into the system or you get some energy out of it. And so what this is on here is a little bit of algebra related between the two of them. And it kind of actually mathematically connects these two ideas. So I know that there's a whole bunch of algebra that's on here that kind of relates to these two different things. So we know that work equals force times distance. And essentially, if you do a bunch of, algebra magic, which you don't really care about the whole bunch, what you end up with is an equation that looks like this one that's in blue here over on the left side, which is that there is a relationship between mass and velocity and work, basically force times distance. So what this actually means is that there's a quantity in there, this 1/2 mv squared. That's what we call or define as kinetic energy. It's the energy of something's motion, and it's 1/2 times the mass of something times its velocity squared. So between the two things, between mass and velocity, the velocity of an object has way more impact on its kinetic energy than the mass of the object is. The mass of the object is important, yes, but the velocity is the key component that's on there. And if you're wondering where the half and the square and all that stuff comes from, it's on the screen right there. You can kind of follow it if you really, really want to. So anyway, the definition of this particular thing, the way that this equation works, is that if we take a look at, I didn't even finish my sentence. Wonder where it went. What this definition is it's called the work kinetic energy theorem. In other words, work or force times difference. Work equals force times distance. Work is equal to the change in kinetic energy of an object. And then the reason why we call this the change in kinetic energy is that we're talking about literally the final velocity squared minus the initial velocity squared. So 1/2 mvf squared minus 1/2 mvi squared, the change in kinetic energy. In other words, when you push an object, when you put force into it and you make it move a certain distance, you're changing its kinetic energy. You're increasing its speed, or it could, I guess, be decreasing its speed if you really want to. But something about that idea of having to apply a force and to move an object across space changes its energy. So basically what this is called, like I said earlier, it's called the work kinetic energy theorem. And it's just literally a connection. It's an algebraic connection between these two concepts, that work is force times distance, that the change in kinetic energy, or that when you do work on an object, you get a change in kinetic energy. In other words, when you do work on an object, you apply a force, move it a distance, you're actually transferring energy to that particular system. And that system could be as simple as, pushing a crate, or it could be doing something fancier than that. But again, this is called the work kinetic energy theorem, that force times distance equals the change in 1/2 mv squared. So between the two of them. When we start to do this sort of thing, it kind of begs the question, like, well, if we can turn work into energy and we're changing something's energy, isn't there other kinds of things that we can do? And the truth is here, though, of course there is. You guys know this, you have experience in your life, that energy doesn't really just stay in one form. There's a lot of different types of energy. Kinetic energy, the energy of something's motion, is one type of energy. And then the other kind of category, general category, something is called potential energy. So when we do work on an object, not only can we change how it's moving, change its kinetic energy, but we can also do work to store energy in an object by, say, lifting something up or bending something or a variety of other things. But we can either turn that work into kinetic energy, or we can turn it into something called potential energy. And potential energy is what they call stored energy. You had to do some work on something, and now there's energy sort of waiting to be released. And a lot of times, again, we think about things as lifting something up, or maybe like stretching a rubber band or doing something along those lines. These are the forms of potential energy. So kinetic energy, potential energy that's something that's in motion is kinetic energy, and then stored energy that's sort of waiting to be released is what we would call potential energy. And there's actually lots of different kinds of energies. I've got kind of a list of them on the screen here. But one of the things that we do know, the law of conservation of energy, is that we can convert energy from one form to another form, and that energy is conserved in these transfers, in these transformations. Sometimes it's conserved in forms that we can use, and sometimes it's forms that we can't use quite the same way. So in a physics context like this one, we're gonna focus more on the kind of useful bits, at least in this chapter, which is something that they call mechanical energy. That's our typical forms of potential and kinetic energy, like I was mentioning earlier. So on the screen up here, there's a bunch of different other types of energy that's out there. A couple of them are potential energy, some of them are more of a kinetic, some of them have kind of a different format entirely. But all of these are different forms of energy, ways that work can be done on a system or by a system. And so when we typically talk about things moving, we're talking about either something's energy of position, which we would call gravitational potential energy, like whether it's higher up or lower down, whether it's something moving, like 1/2 mv squared, which is kinetic energy. We can also talk about elastic and spring energy. So for example, like stretching a rubber band or bending a piece of wood, like a ruler, if you're going to do that, or even the energy that's in a ball that makes a ball bounces is a type of elastic energy or a spring energy that's bouncing around. But then there's all these other kinds too, like the energy that's stored in chemical bonds is a type of chemical potential energy. So basically what a battery is, it's chemical potential energy. If you throw the battery at somebody, then it's kinetic energy, but that's not typically the type that we're referring to. Thermal energy is our big loss type. Thermal energy is oftentimes, you'd call it heat, but one of our huge spherical chicken assumptions, of course, is that when we're doing mechanical energy conservations, that we're not losing anything in terms of heat or friction. That's not true. It's just a not very measurable, not useful form of energy. So thermal energy ends up getting lost to the universe a lot of times and becomes a very difficult type of energy to sort of reharness in a sense. Nuclear energy is the energy that would be bound up within like the protons and neutrons, the quarks and stuff like that within an atom. We can talk about sonic energy or sound energy, which is actually a type of kinetic energy. It's vibration in air molecules, but it's not air moving across space, it's air vibrating in space. So it's a little bit of a different thing than a type of kinetic energy. Vibration itself, like when two cars like crash together, or when an engine is running roughly, there's a vibration in there, and that's another type of sort of non-mechanical energy loss that's happening in a system. Light and electric magnetic energies are another totally different type of form of energy that transfers through space. It's a little bit of a different style. We'll talk light and electric and sonic, some of the stuff actually in the second semester. So for right now, we're just going to be talking about mechanical energy, and specifically, we're going to be talking about gravitational potential energy and kinetic energy. We're not even going to really talk about elastic energy too much. We could, it's just a matter of time in terms of what we've got. So are two different kinds of energies that we're going to be focused on here in terms of our conversions of mechanical energy is potential energy and kinetic energy. We already defined what kinetic energy was. That work is the change in kinetic energy, and the formula for kinetic energy is 1/2 mv squared. Here's our two types of potential energy that we typically talk about as forms of mechanical energy. The big one here is gravitational potential energy, the energy that's stored in the system when you work against gravity. So if I have an object and I lift it up, I've had to do work, force times distance, to get it up to a certain height. And now as long as it's at that height, there's a type of potential energy that's in there. And if I let go of it and it falls, I could be converting that potential energy of height back into motion. That's basically what the whole chapter on kinematics was all about. Free fall was about turning potential energy into kinetic energy and some of the equations that worked with that. We're not going to deal with elastic potential energy in this particular chapter. Again, we're just skipping it. But there's an equation that goes along with elastic potential energy. Just as a real quick aside, the equation there, that 1/2 kx squared, it looks a lot like kinetic energy's equation. K stands for a spring constant. You guys know that certain things are stretchier or more resistant to stretching than other things. So think about two different kinds of rubber band, like a real thick rubber band or a real skinny rubber band. Little skinny rubber bands have a small value of K. Real thick, heavy duty rubber bands would have a higher value of K. If you talk about like a big metal spring, it would have an even bigger value of K. And then X in this case for a spring is the distance, the displacement, how much stretch, either compression compression or extension that you're doing. So it makes sense. I mean, you guys know how, if I'm stretching a rubber band, how much energy I'm going to store in that thing. A, it depends on how far I stretch it. And B, it depends on how stretchy the rubber band itself is, what the characteristics of the rubber band or the spring are. For gravitational potential energy, this is one that you do need to know. The equation of gravitational potential energy, if I could speak, is mgh. M stands for mass, g is acceleration due to gravity, so that's your 9.81, and then h is height. How far up against gravity did you move it? It's basically a delta h, but that's kind of what we're referring to in there. So gravitational potential energy is mass times gravity times the height that you move the object. Again, those are the key ones that we do. So as we're doing mechanical energy conversions, basically we're going to just look at mechanical energy. That truly, yes, the law of conservation of energy exists, and you can convert to all different kinds of ones. We're going to focus on the conservation of mechanical energy, and specifically we're going to focus on the two types of mechanical energy: kinetic energy and gravitational potential energy. Those are the two that we're going to refer to. So basically, the total final energy equals the total initial energy. And again, you can kind of mix and match what form they're in. So at the beginning of motion, maybe you have more potential energy, and the end you have more kinetic energy, or vice versa. But basically it's just a final, the final state equals the initial state. And it's the sum total of kinetic and potential energy at the end is equal to the sum total of the kinetic and potential energy at the beginning. We could throw gravitational, elastic potential energy. We can throw all the other ones in there as well. But for what we're doing in here, we're going to ignore those other parts. We're just going to look at the conservation of mechanical energy. And our big spherical chicken assumptions, we're going to assume that there is no loss in thermal energy. Of course there is. But for the math that we're going to do here, we're going to assume, no friction or no thermal, no loss in that particular format. So how we apply this is, typical kind of roller coaster problems. I don't know if you've ever noticed on a roller coaster. Roller coasters are all about kinetic energy, transformation of kinetic to potential energy. So if you take a look at our little roller coaster friend here, what we actually get is constant transformation of one form of energy into the other form of energy. So if we talk about our little roller coaster up here, I got to get my pen back. Our little roller coaster that's up there at the top. And go find a pen. There we go. So up here at the very top at position W, up there at the very top of it, almost all of that energy at the very top of that hill is in potential energy. Well, where did it come from? Well, you guys know how roller coasters work. They go chunk, 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 and they get up to the top. You have to do work on that particular car to get it up to the top of the hill. So once you've done the work, and the work comes from the machinery that's in the roller coaster itself, but you're going to do force times distance to get it up to the top of the hill. And then once it's at the top of the hill, it can kind of coast on down the hill, and it can kind of go that direction. And as it's going down that hill, it's constantly losing potential energy, right? Its maximum potential energy is up at the top. That's where it's at its maximum height. Because if we're talking about mgh is the equation for potential energy, the mass isn't going to change throughout the course of the system. G isn't going to change through the course of the system. It's just the height that's coming and going. And up here at W, we've got maximum height. So that's our maximum potential energy. And then as it goes down, and it gets down towards, like, say, position down X down here, this is now all basically in the form of kinetic energy. It's where it's going at its maximum speed. You've turned all of that height, all of the work that you did to get up in there, you put it into its positional kind of phase. And then once you let it start to roll down the hill, you're converting that energy into its motion phase, or its kinetic energy. And in this particular case, again, it's 1/2 mv squared. And in this case, you've got your maximum velocity when it's at the bottom of the hill. And so you can kind of see this other little graph that's over here, is that you kind of get this trade-off between the two, that when potential energy is at its highest, generally kinetic energy is at its lowest. You're at that maximum height, but it's not really moving. And then as it goes down the hill, then your potential energy is at the lowest, and your kinetic energy is what's maxing out because it's getting high again. And then you go up to the second hill, as you kind of go up this direction over here. Again, you're doing this trade-off where now you're going back up to Y, you're going back to PE again, and you're reducing what your kinetic energy is. Big question, why is Y always lower than W? Why is the second hill higher or lower than the first one? Well, the difference between W and Y, the difference between those two things, that's thermal energy. That's all that other non-mechanical energy that gets lost. You can never have that same difference in the second hill versus the first hill. All of that energy right there gets lost. Non-mechanical forms. It's usually heat, friction between the car and the wheels. A lot of it is vibration, literally side to side movement. Some of it's elastic deformation. The things are starting to sort of bend and flex a little bit as you go. Sound is another form of energy that gets lost, which is vibration in the air. So all of that extra energy is gone there. So your second hill can never be quite as high as the first hill, because in the real world, non-spherical chicken, you do get non-mechanical energy loss, which is what that changes right there. But again, in general, when you're doing a swing like this, you're going to start off with maximum potential energy, and then you get to maximum kinetic energy, and then you get to maximum potential energy again. A second case of this, by the way, that I did not put in here is the case of a pendulum. That if you have something that's hanging in the bottom and you deflect it over to the side here, so its new form is over on that particular range, you're going to have it kind of swing back that direction. When it's up here and it's at its highest part in the swing, that's going to be your maximum potential energy, MGH. And then when it goes this direction, this is going to be its maximum kinetic energy, 1/2 mv squared. And then it's going to coast back up this direction. And then you'll have your other case back over here, where again, it's back over to potential energy, to MGH. And again, a swing back and forth is a constant transfer of energy between potential energy through kinetic energy, back to potential energy, back to kinetic energy, back to potential energy again. And that swing back and forth. And again, we lose a little bit of height on every swing because you're getting some of that conversion to non-mechanical forms. Typically, it's friction because of air resistance, but vibration and other things like that as well. So again, transfers of energy, when we're solving these kinds of problems, we can solve these problems not necessarily with kinematics, like we did back in chapter 3, but now we can use conservation of energy to solve some of these problems. So the last few slides in here are some examples of some math applications to these, and then I'll be done relatively quick from this. So how do we apply our application problems to this kind of stuff? Pardon me. So here we're going to do work, basically taking a load of bricks, and you're trying to lift it up to the top, third floor or something along the lines up here. So question number 1, how much work does the bricklayer do? Well, work equals force times distance. Okay. Well, how do we do this? It doesn't look like we have enough information in here to be able to figure this part out. But if we're trying to lift up 30.2 kilograms of bricks up to the third floor, remember that in this case, the force that you're doing is against the force of gravity. You're doing work against gravity. So what this actually here is m times g. Again, it's the mass of the object against the force of gravity or acceleration due to gravity times d. I don't know if you remember from the last chapter or earlier this chapter, we said work is also the same thing as m times a times d. That if you're doing work, force is mass times acceleration. So in this particular case, you're working against gravity. Same idea. So in this particular case, it would be 30.2 kilograms times 9.81, which would be our acceleration due to gravity, times our distance, 11.1 meters, and whatever that turns out to be. Of course, I don't have a calculator. My apologies. I'll let you do the math on that. I do not have a calculator for this one. So figure it out. I know you can do the math because, go get a calculator and go multiply. Units for this. Units of work. Work is going to be in force times distance. This is in something that is a Newton times a meter. A Newton meter, the units of this is also called joules, Joule. A joule is a Newton meter. A joule and a Newton meter are the same thing. It's also the same thing as saying a kilogram, meters squared per second squared. These are all equivalent units. Again, typically with work, we will do it in the unit of joules. Energy is most commonly expressed in the unit of joules as well, but Newton meters is the other name for this, which is totally fine. All right, problem number 2, what's the potential energy of the bricks? Okay, potential energy of the bricks. Well, potential energy, PE equals mgh. Well, you'll see that this kind of works out pretty well. In this particular case, the new potential energy is going to be the mass of the bricks, 30.2, times gravity, 9.81, because you're doing work against gravity, times height, 11.1. You'll see these two things are the same thing. And so again, work and potential energy, just like work and kinetic energy, kind of are related to one another. That when you are doing, when you're storing energy in a system, it's because you're doing work against something, either work against its motion, against friction, or in this case, work against gravity. So in this case, potential energy and work are essentially the same idea. Moving on from this, kind of continuing it, whatever our particular values are. this is part 2 and part 3. The top 2 questions are the same from what I had on the previous slide. So what's the kinetic energy of the bricks when they hit the ground? Okay, what do you mean by hit the ground? Well, if I've got it at 11.1 meters and I push them off the top of the bridge, or if I drop them from the top of the ladder, what's going to be the kinetic energy when they hit the ground? Well, think about how this works. If I take a set of bricks and I lift them up to this point, I now have bricks with a certain amount of potential energy that's stored in them. If I drop them back to the ground, I have now converted what was kinetic energy now into potential energy. So if I think about this, conservation of energy says that at the beginning, PE plus KE, so at the top of the ladder, is going to be equal to PE plus KE when they hit the ground. So this is before and this is after in terms of making them equal to one another, conservation mechanical energy. So with this, at the top of the ladder, they're all PE and KE equals 0. When they fall, and they're at the bottom of the ladder now, PE is essentially 0 because they're on the ground, and it's all KE. What this means is that the potential energy from the top of the ladder is going to be equal to the kinetic energy at the bottom of the ladder. So this is mgh, and this is 1/2 mv squared. So if I remember what this value was, and I did it, if you guys did the math on the other one, whatever this potential energy was from earlier, which is 30.2 times 9.81 times 11.1, whatever this value was in joules, that's the same thing as going to be our kinetic energy. So whatever my initial potential energy was, that's now equal to what my kinetic energy is at the end. And once I know what that value is, I can then go ahead and solve for 1/2 mv squared. So I know that 30.2, I'm going to give myself a little bit more room to go here. There we go. Let's see, let me give myself a little bit of space. So back to my pen, 30.2, which was the mass, times 9.81, which was gravity, times the height, 11.1, is equal to 1/2 times the mass, 30.2, times v squared. These cancel out, or you can just figure out what the math is on there. So 9.81 times 11.1, this guy, I'm going to be multiplied by 2 to get it over there, equals v squared. And then all you have to do is just take, do your math, figure that out, and then you can figure out what the velocity squared is. And in some ways, it's actually easier to do this than it is to try to figure out which kinematic equation it is. When you're trying to figure out the kinetic energy and the final velocity, a lot of times this is just a little bit easier. It still works with the kinematics equations, by the way. And if you actually go back and look at some of those old kinematic equations, they're exactly like this. Does this look familiar to you? Vf squared equals vi squared plus 2a delta d. It's the same equation. And that's why this particular thing works. These are all related to one another. They all come back around. So a lot of our kinematics equations from way earlier are related to this kind of conservation of energy stuff, and the fact that work equals force times distance, and work is the same thing as doing potential energy, storing potential energy, which is the same thing as changing something's kinetic energy. They're all interrelated. It's kind of creepy. I hate it. Okay. And then here's an example for you to take a second and see if you can kind of figure out what this is. So I'm going to let you hit pause again. I don't have a calculator sitting here next to me, so I'm going to I'll set it up here in a second. Hit pause and see if you can figure this one out. You've got a rock perched at the edge of a cliff. Now I want you to answer this one using conservation of energy rather than trying to remember what the kinematics equations are. It's actually easier in this case because the formula is a little bit easier in terms of figuring out what they are. So go for it. I'm going to let you guys hit pause, and then I'll come back and answer it in a second. Again, I won't be able to do the final answers, but you'll figure it out. All right. So solving this particular problem, what's the potential energy of the rock? I'm assuming we're meaning at the beginning. Potential energy here, PE equals m times g times h. So our potential energy of our rock, PE up here, is going to be equal to the mass of the rock, 20 kilograms, times g, 9.81, times h, which is 100 meters. I don't know what that value is. I'm sure you've got it somewhere. It's like 98 something or other. But the answer to this one is going to be in joules. It would be whatever that final value is. Sorry. So when you want to figure out what the velocity of the rock is when it hits the ground, I'm talking about down here, rather than reaching in towards kinematics equations, now we can just use the fact that whatever this PE was here at the beginning is going to be equal to KE at the end. So I know whatever this value was, which you guys have in front of you, I now, though, at the end of its travel, by the time it hits the ground, equals 1/2 mv squared. So I know what this is, 1/2. I know what the mass of the rock is, which is 20, and then I'm just solving for what v squared is when it hits the ground. So this is going to be 10 v squared, and then take your, divide by 10, and then take your square root. So it can be a lot easier to solve your kinematics equations to solve for final velocity. Again, don't forget to take the square root so that you can get the correct final velocity when you're doing these ones. So again, using conservation of energy rather than kinematics. On the quiz that's going to come up on Friday, I'm going to ask you to do a problem like this, and you're going to need to show me this with conservation of energy. Yes, I know that you can also solve it with kinematics, but I'm going to ask you to specifically apply this law of conservation of energy, the transformation of energy between the two of them, so that I can kind of see how the two of them work. So just as an FYI, this also makes it a little bit easier too if you do two-part motion. By the way, if you've got, say, like a rock that's falling and then it kind of falls again. So if you've got a rock that starts up here and then you're going to hit here first, and then it's going to hit even further down. Sometimes being able to figure out what your velocities are at a spot like this is a little bit easier because you know what your potential energy transformations are. So anyway, just as an FYI, sometimes it's a little bit easier to do this one. Okay, last part. The last part about this is specifically applying this law of conservation of energy to collisions. With collisions, from one of the previous units, you now know that momentum is always conserved. Velocity is not necessarily conserved in collisions, but momentum is conserved. And furthermore, in certain types of collisions, kinetic energy is also conserved. Not potential energy. Again, a lot of these are moving in different ways. But the key things here is to kind of keep in track of two different factors when we're talking about collisions. Number one, momentum is always conserved. So you've got mv plus mv equals mv plus mv. So this would be your two different objects before and your two different objects colliding afterwards. Momentum is always conserved. Does not matter what type of collision it is. For kinetic energy, though, this only is conserved in what they call perfectly elastic collisions. Perfectly elastic collisions are hard body collisions. So it's like the first two pictures on the bottom left here, like a bowling ball is a pretty close to a perfectly elastic collision, or like a Newton's cradle, like this kind of thing, is also considered to be a perfectly elastic collision. We've got two hard bodies where they're bouncing off of one another. The reason why these are called perfectly elastic is because they're literally just bouncing. The elastic part comes from the idea that there's no deforming. So if you've ever seen super slow-mo of like a basketball or baseball or a golf ball or something like that hitting a surface, the ball like deforms. It like smushes flat before it bounces back off. So it comes in round and it kind of goes a little squishy and then it bounces back. And that's actually what the deformation is. And in that particular process, you lose some energy. You lose some of that energy in the deformation process. Basically, the materials of the ball itself absorb some of that energy, turn it into internal vibration and internal potential energy that doesn't get then turned back into kinetic energy. You lose some energy as heat and things like that as well too. So think about when you drop like a ball on the ground, like that first bounce comes up pretty high and the second bounce is a little bit lower and then the third bounce is lower yet. That's because those are not perfectly elastic collisions. If you did a perfectly elastic collision, like think about like a super ball or even certain types of golf balls can be fairly elastic. When you drop it, it almost comes back up to your hand. That's a perfectly elastic collision where it's coming back all the way. Imperfect collisions or inelastic collisions are what we call sticky collisions. So like a car crash is an inelastic collision where they're going to crash together and there's going to be deformation. The parts of the car are going to wrinkle up and bend and you're going to lose a lot of energy and sound and all that energy is going to go into the crumple zones of the car. I have a picture of an arrow hitting a target right behind my picture right up above here. That's another type of an inelastic collision where the two hit together and become one and travel as one. Football tackles are inelastic collisions or imperfectly elastic collisions. You're not really bouncing off of one another. So in these particular cases, when it's a more realistic type of a collision, kinetic energy is not conserved. In these more realistic collisions, some of that energy is not saved as kinetic energy. It's turned into thermal energy, deformation, vibration, sound, all of that kind of stuff. In the physics world, we talk about perfectly elastic collisions. It's where they're literally bouncing off perfectly. And a lot of the questions are going to ask you things like use conservation of momentum, figure out what the new final velocity is, and then tell me how much energy is being lost in the process. How inelastic is it? So here's an example of our two little skater friends here. Ooh, I don't know what I just drew on there. Sorry, did not mean to be Looked like I was doing something funny there. So with these guys, here's an example of this sort of a collisions problem and how we apply to it. So we've got ice skater number 1, who's 54.5 kilograms. They are moving, and then they collide with a second ice skater who is motionless. So they're sliding together then across the frictionless ice and looking horrendous as they do it. So question number 1, what's their velocity after the collision? This is a conservation of momentum problem, even though it doesn't say it. Momentum is by far the easiest thing to use when you're doing collision problems. So you've got mv1 plus mv2, so there's our two skaters, is going to equal the two of them together times vf. So this is skater number 1, this is skater number 2, this is them together. When you do a collision like this, using conservation of momentum is usually the first thing that you want to do. So we would do 54.5 as our first skater, and they're going at 3.2. And then our second skater is 44.7, but they're not moving at first. So this is going to end up going away. There's no initial momentum for that second skater. And then afterwards, we've got their combined masses because they're traveling as one. It's an inelastic collision. That plus 44.7, and then you figure out what your VF is. So again, I don't know what these values are. This is roughly 150 over here. It's like 160 something. I'm not sure what this one is either because I don't have a calculator there. But you can solve for whatever your VF is to figure out what those numbers are. So literally just multiply those two together, add those two up, and equals VF. Just do your algebra and solve for whatever your VF is. Okay. How much kinetic energy was lost in the collision? Okay, so in this one, when you're going to do your kinetic energy problem, what you're trying to figure out is, for this sort of one, is what's your final kinetic energy versus what's your initial kinetic energy. So your change in kinetic energy, KEF, minus KEI. In this case, I can almost always tell you that the answer to this one is going to be negative because you're losing energy from the system. Your final kinetic energy is going to be less than your initial kinetic. Man, if it's more, you've done some magic. I don't know how you got more energy into that system. Something weird is going on in there. So in terms of doing this, to figure out what your kinetic energy is, you would do 1/2 mv squared. All right, well, kinetic energy 1/2 mv squared is our equation for Ke. So in this particular case, our mass is our combined mass. This is the final energy of the system, is these two skaters sliding together. So this would be the 54.5 and this would be the 44.7. It'd be those two combined. And then you'd take your VF from this previous problem and square it. Then you would look at what your initial kinetic energy is. So we take a look back at our kind of original problem. In our original part of the problem, only one skater was moving. The other skater wasn't moving. So we would literally just look at what was the kinetic energy of the one skater that was moving, which was 54.5. And then their velocity was 3.2. Make sure that you square it. One of the common mistakes that students do is that they kind of mix and match the formula for momentum, which is just mass times velocity, and the formula for kinetic energy, which is 1/2 times mass times velocity squared. So make sure that you actually square it. And so by the time you're done with these two things, again, you'll get some sort of an answer. This is just this is a number, put it in there, calculate it all, and you'll get some sort of a negative, it won't be a -0. You'll have some sort of a negative value that'll end up out of this. Again, whatever it is, it'll be energy lost. What percentage of energy was lost? If you want to do the percentages, you literally do the two numbers basically divided by each other. How much did you start with? How much did you end with? So you're going to take your VF or your KE final divided by your KE initial, and then just times 100. You'll figure how much was lost by that. You'll see like you either have 80% left, so I lost 15%. If you want to, you can take this answer, the amount that was lost, and put it over your KEI. And again, you'll get a percentage lost. Don't tell me what percentage is left. The question here is asking you what percentage was lost. So you should have how much did you actually lose. Where did it go? It went into deformation, their bodies folding and then sliding across the ice, that kind of stuff. So there you have it. When you're dealing with these sorts of problems, we now kind of talked about our different types of energy. So we talked about work and how work is related to energy. So that number one, that work and kinetic energy are directly related to one another, that when you do work on an object, the work done on the object is equal to its change in kinetic energy. We also talked about how work and potential energy are related to one another. That when you do work on a system, if you're not turning it into motion, you can store it as a type of potential energy. Oftentimes, the way we'll talk about it will be gravitational potential energy. Although if you're stretching an object, you could be talking about elastic potential energy. We talked about some different types of energy, mechanical and non-mechanical energy, and the fact that energy is transformed from one form into another, that when you do conservation of energy, that the total amount of energy that's present stays constant, although it's going to change what its form is. And then we applied some of those different things to being able to deal with some of our different types of problems. So again, just the reminder that when we're doing these, that you've got a couple little quick formulas to use, and then that when you're doing these kinds of problems, sometimes using conservation of energy is actually an easier solution method than using kinematics equations is, even though they are directly related to one another by algebra. But they're directly related. But like I said, sometimes just using conservation of energy, converting from potential energy to kinetic energy is an easier way to go. So there you go. That's our last unit of the semester, man. That is it. We are done with first semester of physics. No more kinematics, no more force and motion. Next term, we talk about energy and waves and things like that. So I hope you've survived the semester intact. And that's it. We're out. So spread kindness, not corona, and I will see you guys later on in the week. Have a good one, you guys. Bye.